the web, this seems to be a very small web, has 20 million docs, and we were kind of expecting 20 million different words. Okay, so this is how the map reduce thing will work now. Oops. So what will happen, just the way we did for letters, we will divide the documents into chunks. The chunk could be divided in terms of the number of files, or it could be based on the number of the size of the input. So we have to split the input in some fashion. So in what fashion, it is up to the programmer or developer. Sometimes if you ask the system will do it for you based on the default split size. So in this case, Hadoop will do the split based on 64 MB, because we're dealing with large documents. Each document is of could be more than 64 MB. So it will split each file into blocks of size 64 MB, and all these blocks are passed as input to a map task. So there are several machines. So all of them are ready to do map task, and then each of these input is passed to this machine. Each of this split is passed to a machine. So in this machine, we start running the map task. So what the map task does, it opens the file, reads every line, and breaks the line into words. And then for every word, it counts. Let's say if Reddy has occurred once, so Reddy is one count. So if it has occurred in more than multiple places, it keeps adding. It doesn't add the count, it just keeps the list of all the words and how many times it has come. Okay, is it clear?
No, can you please explain this?
Yep.
Okay, so each map task opens a document, and once it opens a document, it knows that it is it is reading a document, and within that chunk, within that split, it opens a line. It splits the line into words, and for each word it counts, and it marks each word with, okay, this word has occurred once, this word has occurred once, like that. Okay, so the output of the map task is a list of words with their counts. Is it clear? Across all the documents.
But we are trying to find just the ready. But we are just trying to find our aim is to find the word ready, right? So why are we counting all other words?
No. So we are trying to count all the words that are used in the web, not just ready.
Okay.
Ready is one such word.
Okay.
Okay. Just like we're processing all the letters, we're trying to process all the documents and trying to count all the words, and maybe at some point we will find out what is the most frequently top 200 words used in the web very frequently, right?
Okay.
That could be the report. But for that, we need to first count how many times each word has occurred in every document across 20 billion documents in the web. Okay, is it clear?
Yes.
Okay, so now the output of the map is basically a list with words, and each word occurring how many times. So let's forget a little bit about combine for now. We'll come back to combine just a few minutes later. Now that I have list of words and counts, I do a shuffle. So from different machines, just like I get bins from different postmen, I do a shuffle. So for all the words that were from different documents, I do a shuffle from all the tasks, and then put them together. Right? It is like putting all the letters into a common bin going to a particular state. So all the words from different map tasks, right, are shuffled and put into one common bin or put into one common place, right? This is also very important to understand now, because now it is coming to reality. So let's say that there are three words that has occurred. For example, Hadoop, big data, and admin course. Let's say these are the three words, and they have occurred in multiple documents. So in the first map task, you would see the 3 words here, and in the second map task also, if some other document has it, you will also see those 3 words. And if it is so popular, the third document also will have the same words. So since we're not doing combine yet, right, we'll come to shuffle. So the big data word from the first map task is counted here in the shuffle, is put together in one common bin. In the second map task also, the number of times the big data word has come from the second map task is also pushed to the shuffle, and you keep all the words that is related to big data in one place. That is called shuffling, right? Is it clear? And then once I have the shuffle, so for this big data, now I know that all the big data, all the words that all the documents that has the big data is in one place as part of the shuffle. Then I'll pass it as a reduce. Then what I'll do, I will count all the word for this big data. Now I know that it has occurred 100 times. So I'll count 1 to 1 plus 1 plus 1 like that. So I'll get 100. So the reduce output would be saying okay, big data word has occurred 100 times in all the documents, in the 20 billion documents that we have searched. Is it clear?
Yes.
Okay, so combine will do little bit of optimization. So what combine will do is, suppose the same big data word has occurred in 20 documents within the first map task itself. In the first map task itself, big data word has occurred in more than one document. So instead of waiting till the shuffle operation to be combined, map task can do an intermediate shuffle, combine within the set of documents that it has. So that will optimize so that the shuffle can be more efficient. So call the words that occur big data within the map task itself. It will combine first before passing it to shuffle, so that shuffle can handle less sorting or less merging before it passes to the reduce. Okay, so that is the objective of a combined task. So in the case of a postman, right? Suppose if one postman gets letters to California. One second. Okay. So if a postman has letters to California, right? So what he will do, he will combine them into one bin before it goes to shuffle, right? So that is kind of a combine operation that happens. All right, so let's move on. If there are no questions, we'll move on.
Ready?
Yeah.
Ready? This is Shruti. I have a question.
Yeah.
In the combine method that you explained, I didn't get the functionality of combine, since as we are traversing the whole document, we are getting the count of each and every word. So why
Right.
do you want to combine? Because at the first place, you are getting the count. So the
So let's
kind
say
of
that-
task you explained.
Right. So
Yeah.
in this case, what happens is, Shruti, let's say big data has worked in has occurred in 10 different documents. Okay, in one split, in one input. So the output of a map is big data word with one count as 1111 like that. Okay, so I have not combined or I have not counted big data together yet until I go to the shuffle mode. I just know the map does just know that big data has occurred, so I'll tag 1 to it. So big data has occurred, I'll tag 1 to it. Hadoop has occurred, I'll tag 1 to it. I have not combined, I have not added for every input within the map task. I have not added that big data, if you add together, it occurred 10 times. So that is the combine operation. Okay, so what it means
You're trying to
is
say
So that's what we
that-
are doing. That's what we
Sorry.
are doing right here. I mean, we are increasing the count whenever we encounter the word big data.
no, we are not increasing the count.
Right?
Yeah, we're not incrementing the count because we are not incrementing the count. Remember that we are only tagging the word with 1. Okay, because we'll come to that mechanism later. We are not incrementing the count in the map task. We are only detecting big word as big data word has occurred, and then we will tag that word with a count of 1. Like that, big data has occurred 100 times, 1000 times. So I'll just tag it to big data 1 like that. So I'm just giving you the list, right? Just the letters. I'm not counted yet. I've not summed together. Usually the sum happens in the reduced mode. So before I go to the reduced mode, I can do a little bit of optimization where from every input, I can combine the output together. So if big data has occurred 10 times, I'll just say big data 1 plus 1 plus 1 like that 10 times, and I combine it, and I pass for this big data word has occurred 10 times. I pass that information to shuffle, as opposed to the same big data occurring big data 1 like that 10 times. Okay. Is it clear? We'll come across this again. Okay, don't worry. So if it is not understanding, you will come across this again. So
Reddy,
now,
another doubt.
yeah.
Is
Go
it
ahead.
possible, like, we're not, it might happen that the first map gets the chunk of data which has those words a lot, and second does not get, second sits idle, it does not get words. So do we do something
Right.
here that, everybody gets the equal?
Yes, it is
Instead,
possible. Yes, it is possible. That's the whole thing about this 20 billion documents. Any kind of word come in any document, and there could be section of words that can come in one input which are completely related to each other. It's possible because you picked up those documents from certain locations, and it so happened that they're all related to big data. So one map task may count big data more frequently than some other map task which is discussing some words related to chemistry, right? So those things can happen, but we're not segregating the words here. We're just counting the words. So the processing, the compute, the map task is doing a compute. Compute is nothing but read each line, split the line, tag the word with count 1, and then pass it to shuffle. If there is a combine operation in the middle, you tag the word, and then the next step is within that map task, whatever you tag, you add them all of them together in the combine operation and pass it to shuffle. And then after the shuffle is done, then you add all the words that are occurring from all the inputs into one place. Okay, is it clear?
okay.
Yeah, we'll come back. So yeah.
Yeah, actually you said in map you count all the words, and then in combine you will tag the word with one, and then in shuffle you will add all those things. So
No.
yes,
Okay, so let me repeat. We don't do that way. So what I'm trying to tell you is just like the postman, he takes a letter, and then for this zip code he tags the number 1 to it. He tags the number 1 to it for that zip code. Okay, and then he doesn't do any adding in map and combine operation yet. Okay, let's forget the combine for now. So he takes the letter and tags the count 1 to that letter or to that zip code, and then passes it to shuffle. Right? What shuffle does is all the zip codes that are together will be put into a common bin. Right? It doesn't add. Shuffle doesn't add. Shuffle is just keeping the data together. It's just putting everything into one bin. But how many letters are there in that bin? It doesn't care. Out the reduce operation is saying, now I got the letters for this zip code, let me count. That is how it works. Okay. So the optimization that we're trying to do is within the same bin, if there are letters to the same zip code, instead of waiting for the reduce operation to count, I'm combining in the map task itself for that zip code and then sending it to shuffle so that I can do less shuffling. Okay. So
When I have a doubt, is it like summing of the count of the data is done twice, like in combine and then reduce?
No. Okay, so let me go to the next slide. I think this is what it is. Okay. So you have an input, right? This is how the execution happens. You have an input. It is divided into chunks, correct? And each chunk is passed to an M task, which is a map task, correct? And the output of a map task is key and value, K1V, K1V, K2V, like that. So K1 is the word and V is the count. K1 is the same word and V is the count. K2 is the word and V is the count. What is this count? This count is 1 in this case. It is occurring once like that. Okay. Similarly, in the other map task, you don't see any words at all. In the other map task, you'll see K1, V. So the same word K1 is occurring once. V is 1 in this case. Similarly, the other task K3, K4, K5, those are the words, right? So this is the output of a map task. We are not counting. For example, in the first map task, the word K1 occurred twice, right? The first one says V and the second one also says V. Sorry. So it is 1 and 1, but we are not added together, right? So the next operation is shuffling, right? The next operation is shuffling. What I shuffled is that I took all the K1s coming from all the map tasks, I grouped them by key, and then if you see the output of the group by key or the shuffle operation is K1 says V like that. It occurred 1, 2, 3, 4 times. I have not counted. I'm just giving a list, right? I still don't know how many of them. So I said K1, then V will be 1, comma 1, comma 1, comma 1, like that. Okay, so I have not counted them to, I have not added 1 plus 1 plus 1 yet. Okay, similarly, K2 has occurred only once in all the documents. K3 has occurred twice, 1 and 1. K4 has occurred 1, 1, 1, 1. K5 has occurred 1. Now, if you see this whole list, the key and the values, right? In this case, if you look at the postman example, so all the letters going from New York to California, let's say that California is the key, state is the key, and all the letters, this V is each of this V represents a letter. All of them are passed to the reduce operation. So what the reduce operation is that now you have a key and list of values. So what you do with it, it depends upon your business analysis. What you want to do with that data. So my business analysis says, okay, I want a report of for the past 20 years, how many letters has gone to California from New York. So I just want a count. So I'll put a count. Okay, K1 is the state K1 in this case has got maybe 100,000 letters every day or something like that. So in the case of words, K1 has occurred 4 times. So that's what the reduce operation does. Okay, let's go one more step detail. Okay, so here. Okay, so you see map task 1, map task 2, and map task 3. Okay, so this is little detail. We will cover slightly different. So what this one is saying, even though it's map task 1, you're seeing M, and M in each map task. So this M is nothing but, right? Once you got the split, right? Once you got the split. In this case, once you got a document, you're opening a line. You're opening a line and splitting into words and tagging the words. So each line is 1 M here. Is it clear? Within that big document, each task, map task 1 is processing a big document. Within that big document, I read one line and I split it. That is this M in this map task 1. Similarly, another set of documents goes to map task 2. I open the map task 2. I read a line, map M, like that. So what it is depicting is that the map operation is happening for every line in the document, right? So again, the output of each of these maps are, right, keys and values, right? And then, so there is a partitioning function that we will deal later. So just to get you the truth, so the partitioning function in case of postman is the state name, right? So for every state, we want to go to a bin. So if there are 48 states, there will be 48 bins. So the partitioning function will say, okay, all the letters with this zip code has to go to this bin. That is the partitioning function. So generally, if you don't have a partition function, you can specify the number of reduced tasks. And if you don't specify the number of reduced tasks, by default, the system will assign some reduced tasks. So if there are 48 states, the number of reduced tasks would be about 48, because the partition function returns so many unique states, it will become so many reduced tasks. In case of words, if you want to do a partitioning function by word, which is very inefficient. So in that case, it will be each unique word will get into one partitioning function, which is very inefficient. So we don't do that way. We only do it for some cases. Now, once the data from the map task is done, we go to the reduce task. In the reduce task, we do a sort and group, right? And then pass the key and values together to a reduce task. And the reduce task can just count. That's how it works. Okay.
Whole process is synchronous. Like if the combine of all the maps have finished, then only we start with the shuffle, or shuffle starts as one map has finished its job, combine has been done.
Yeah.
So then
Right. Good. Right. So there is an optimization that happens as the map is progressing because we're doing shuffling. So it keeps the reduce task will keep taking whatever data that is available in the map, and then so the map and reduce can be parallel too, depending upon your task. Generally, for most of the cases, it is parallel, but sometimes if you have to wait till the output of map is cleared, sometimes some algorithms, some tasks need the reduce operation to start only after the map operation is complete. In either case, the task will not be complete until unless all the map operations complete the data. Okay, so in order to save time, sometimes the reduce operation starts and takes the partial output from all these map tasks and start processing.
okay.
So that is the area of research in Hadoop, how efficiently they can start both map and reduce parallelly and then get improved performance, right, without worrying about messing up the data. So again, we are covering map reduce because the map reduce is the money making machine for Google. They use this effectively to index the web. They use this effectively to index the web, to search the web, to do variety of tasks. So again, all the algorithms that we use today may not fit into this kind of split and reduce operations. More than 80% of them will fit, but the rest 20% may not fit into this model. But if it fits, then because it is compute intensive, it can be massively parallelized with thousands of machines, right? You can do this task with thousands of machines, and then you can get output. So again, these map tasks may be 20,000 map tasks, 30,000 map tasks. Reduced task would be few hundreds, right? So we're looking at a very huge data. We're not looking at a very small one file where we look at it, right? That traditionally one machine can process, and then we can do that. But here we're looking at huge data. That is why we have to deal with such a kind of a framework. Does it answer the question? Yeah, does it answer the question?
Yes.
Partitioning will give you ability. See, it's an optional thing. It's an optional thing. It will allow you to partition your map output into separate bins. For example, if what we want to do is, in the case of a postman, we want to partition all the letters based on the state zip codes, right? So that is a partitioning function. If you don't partition that way, then what happens is that we don't, I mean, you want multiple outputs. In this case, all state letters have to go into one bin. That is kind of partitioning. If you don't do that, then only one reduce task will still do the counting based on the key, right? But you will see all the output in one file. You will say the state has 1,000 letters, right? Like that, this state has 1,000 letters. The same state has 1,000 letters in one case. Again, the same state has another 1,000 letters in one case. But if you partition, it will make sure that all the related data goes to a common bin. We will address some of these concepts again. Okay. So basically, in order for you to get multiple outputs, you need to partition. Otherwise, you will get a single output. Is it clear? So when you do an admin course, right, people will write map and reduce tasks only. So again, this is very important. You should remember. You don't have to know much about what is happening inside, but you should know that the developer, when he writes a code, he will not even bother to split it, because system by default takes some splitting. He will only have to write when he gets that line from the document how to split it. And after splitting, if he gets 20 words in one line, take each one word and tag it, and then write that whatever he has tagged right into an intermediate stage, right into a storage where he can remember that, and then the same data can be passed to the next step for shuffling efficiently. Okay, so in this case, the developer writes only 3 lines or 4 lines of code. What are those 4 lines? Take the line, split into piece, tag each word with a count. That's all he will do in map operation. Similarly, in case of reduce write, he will write 3 more lines, which says take this word and add all the values that is coming 1 plus 1 plus 1 like that, and then write the sum into the system. That's all he will do. So total map reduce operation that we did is about less than 10-15 lines here. So map is about 8 to 10 lines, and reduce is about 8 to 10 lines. And with this, just 20 lines of code, we are trying to massively parallelize searching of words across several million documents in the web. Is it clear? Okay. So this is more of generalizing. Again, it goes to the programming model. So you guys don't have to get into more detail. But basically, input and output. Input is again, each set is a key value pairs, right? In case of a map, if you see, it's written by user, takes an input pair and produces a set of intermediate key value pairs. So if you see here, it takes an input and produces key value pairs. Okay, key value pairs. So there is one more thing that he's saying. Map also takes input pair. Okay, so if you look at this, in the case of a split, in the case of a document, right? So the map is taking line by line. Map is taking line by line. So, but where is the key inside this? The value is the line. The key is usually the size of the split. The size of the split that each map task is trying to do is the key generally, or you can use file name. So the key could be anything here, and it doesn't matter because we are not worried about the key. We are only worried about the values. So the map reduce library groups together all intermediate values associated with the same intermediate key. Again, see, this slide is taken directly from the Google paper. This is not very illustrative. I have a different slide. We will run through this one more time so that you guys are very clear. And those slides are very clear in terms of explaining the map reduce. So you will get some of your doubts cleared. Okay. The reduce operation, again written by the user, those few lines of code written by the user, accepts the intermediate key and set of values. So it takes the intermediate key and set of values. And then you can do merges together these values to form possibly a set of values. 0 or 1 output values produced for reduce function. Intermediate values are supplied to the users to reduce function via an iterator. When you say iterator, just imagine that you're having iterator is like this. So it is a concept again. You will see many times in MapReduce. You have to understand that iterator is a programming name. It's a kind of a concept where it is like in case of a bin, if postman is given a bin, right? You take one letter, right? And you take the next letter, So the machine, in order to take letter from the bin one by one, it uses this iterator, right? It says, give me the next value, give me the next value, give me the next value. So that process is called iterating. So in the programming model, it's called as an iterator. So whereas here, we take the letter by hand and look at the JIT. So that taking the letter by hand is called iterating. Okay. So what it is basically is that the intermediate values are supplied to the reduce function is the key and the values. And if you want to read the values, you have to use the iterator in the reduce function. This is a little bit of detail. but you will see. So allows the handle to list of values too large to fit into memory. So again, it is possible that the number of words. So if you have, again, somebody asked me why you need partition function. Sometimes if the data is huge, it may not fit into one machine, right? You want to split into multiple machines. Again, the intermediate output also you want to split so that you can do this reduce operation very efficiently by multiple machines instead of one machine. Okay. Yeah. So here it is. So again, the word count, counting number of occurrences of each word in large collection of documents. So the map takes a key and a value. So for each word W and value, we are tagging that word with 1. Right? All of you following me? There's a map. Second bullet, for each word W, in that value is a line. You split the line, right? And then you tag the word with 1. Whereas in the case of reduce, what you're saying is you're getting a key and a values. So and then third bullet in reduce, for each v in the values, we are saying result is equal to result plus parse int. So we are adding the sum and then we are emitting the result. So let's take an example here. Let's say map is like this. So map task 1, 2, and 3, right? So A is occurred twice, B is occurred thrice, C is occurred twice. So again, when I say A is occurred twice, remember we are using a combine here. Okay. So if you don't use a combine, in the same map task, you will see A, 1, 1, 1 like that. But since I've used the combine operation within the map task, it already added A has occurred twice. Okay. Now in the reduce operation, if you see, it is divided into 2 reduce tasks. So wherever A is occurring, one of the reduce tasks says A is equal to 2. In case of B occurs thrice in map function 1, occurs once in map function 2, occurs 1 in map function 3. So in the reduce operation, you will see 3 plus 1 plus 1. Similarly, C and D and other words are being added. Okay, so that's how the map reduce operation works. So this is, I will skip this because if you're not having programming experience, this will be Greek and Latin. So, but we will address this in a more simpler way later on. Some of the other examples that Google does in their paper, in the paper that they discussed, is distributed grep. Right? You want to find for a pattern. You want to find for a pattern in the document, not just the word. You want to search for a pattern in the 20 billion documents. So that is called distributed search.
Hello.
Yeah.
Ready? Yeah, I was
Yes.
not able to hear your voice for the last slide. Can you please repeat?
Okay. So since when did you miss? Which slide did you miss? Did you get
this one?
You're
No.
not able. You didn't get this one?
No.
Okay. Can you hear me now?
Yes.
Okay. So basically, what we're saying is each map task has this word A, B, C like that, right? There are 3 map tasks in this case. So if you have not used the combine, optional combine, then the output of first map task would be A1 like that. Since we use the combine within the map task, it combined all the A's together and said 2. Similarly, if you have not used combine for B, so it will be B is occurring 3 times. B1, B1, B1 like that. Since we've used combine, so all the B's are added together in one map task. So B is occurring thrice in the first map task. Similarly, the second map task, B is occurring once, C is occurring once. Like that. So this is again, if you see, Postman, right? All the letters going to California. Let's say A is California. So all of them are added to one bin. So that is how it is. Correct? So in the reduce operation, you're combining or shuffling, merging, sorting all the bins together. So all the A's will go to one reduce task, all the B's will go to one reduce task, all the C's will go to reduce task. Like that, in this case, there are 2 reduce tasks. They have divided the data into 2 parts: A, B, C, D in one reduce task, E, F, G, H in the other reduce task. So wherever A is occurring, is passed to reduce task 1. Wherever B is occurring, it is passed to reduce task 1. In this case, B occurred thrice in first map task, once in second, and once in third. So 3 plus 1 plus 1. That's how it works. Is it clear?
Yes.
Okay. So I'm skipping this again. So I was only trying to tell you there are a lot more examples that Google has used. So one of them is looking for a pattern in documents, not just words. Distributed graph, count of URL access frequency. How do they know which URL is the most frequently accessed URL? So they will count how many times the people have actually searched for something and they get a URL, and then they have actually clicked that URL and they read that URL. So that is the count of URLs access frequency. Reverse web link graphs. I think this is specific to Google. I don't know what it is. Term vector for host, inverted index, and distributed sort. These are some of the problems that Google has solved using MapReduce programming model. So typical environment at Google, again, this is more from the administrator perspective. So each machine will have a dual processor running Linux with two 4 GB per machines. Okay. So, and then the network card is about 100 megabits or 1 gig per second. Today, if you're already doing administration, you know that minimum we have a 1 gigabit network within the data center. And each cluster consists of hundreds of thousands of machines, and therefore machine failures are very common. Storage is provided by inexpensive hard disks attached to individual machines, so that the SATA disks as of today. Earlier there were IDE disks. They were not going for RAID disks. They were just taking bunch of disks. So the distributed file system is developed in-house to manage the data on the stored disks. So we'll discuss distributed system in more detail. File system uses replication to provide reliability on the top of unreliable hardware. Right? The file system basically gives some kind of comfort level, so that even if a particular machine fails, you will still be able to access your files. So that we will discuss further later on. User submits jobs to scheduling system. Each job consists of set of tasks. So if Google has about 5,000 employees, all of them will be working on multiple different algorithms. So they need a way to submit each of these MapReduce jobs independently of each other, and all of them needs to how many machines are being used, right? So you will also see, okay, this is the capacity of the cluster in terms of the map tasks. So in the capacity of a cluster is determined by how many map tasks in totality cluster can execute on point of time. So if you submit more jobs than the capacity, then you need the concept of queuing. So you have to queue this request. Once the load is down, once the map task becomes free, then it can take the additional load from the queue. So at some point in this class, we will discuss about 3 different kinds of schedulers. So the first one is first in, first out, very default scheduler. First job which is submitted will get the first priority to process. So there is other schedulers called phase share scheduler and capacity scheduler. They've been written, tested, right? So those things we will know. We will see how to configure as an administrator, and that is what we will do subsequently as we move forward. Again, the same thing, execution overview. So let's get very simple here. It's a little bit detailed. So you see the input files here on the left hand side. It is split into pieces. Each split is passed to a worker task. It is nothing but a map task. So map task some operation, and it saves the output of the worker in a small file system, right? And then all workers save the data, right? After that, a shuffle happens. So whatever is saved is passed to the reduce phase, where you have 2 workers. So in the reduce phase, you do a shuffling, sort, and merging. And then what reduce does is just write the total sum into the output. Is it clear, this picture? So don't worry about the top portion. We'll come back. This is a little bit of fork and execute is how the system creates the worker thread. So in this case, we are assuming the worker threads are already there, and the threads have been created. So who creates them? The master threads. The master creates those worker threads already, right? So the master also assigns. He assigns this split will work with this worker. So the master assigns the map task to each of the split here. So again, I repeat this. So we'll do one more round with a more detailed map reduce in subsequent class, so that you will get a good understanding. But you just remember that the splits are being done. Splits can be by size, or could be for the file name or set of files. Since the files are huge, generally it is by the map task, in this case a worker. The output of worker is saved intermediate output, which is saved in the local disk of that particular worker. From there, the data is pushed to another worker, which is the reduce tasks. This is where shuffle, merge, and sort happens. And then the worker just counts the occurrences of the word and writes the output to a file. Okay. So yeah, so this is what we discussed, how a worker and map task gets executed. We can go through this. We will discuss this again. This is more detailed into programming. Okay. So if someone needs, you can go through this. If you have any questions, we will address. Okay. Then fault tolerance, right? So this also we can discuss. We can discuss little bit here, right? So what if a worker fails, right? So how does that work? So if a worker fails, what will happen is we have seen that in one of the picture there is a master. So the master and the workers keep talking to each other in periodical fashion, exchanging I am live messages. But if the worker fails goes down, then what happens is the supervisor who is allocating the work to the postman for sorting will reassign the chunk of letters to some other postman. Okay. You may ask that what happens if he has already started. So in case of postman,